What's going on, guys? This is going to be the rest of multiple dose. So I would just want to start by kind of reviewing the last video. You can ignore all these graphs for now, but I just want to look on the right side. And it's just three equations that I have. So we know, the accumulation factor is S, and that's really important. Basically, just it's kind of like a shortcut for us to find whatever C max is at a certain dose. So if you want the C max at dose number 7, all we need is the accumulation factor at 7, where n is the what number dose it is. And then we have accumulation factor at steady state. So that's what happens when after a big N, after a big N, what's going to be your accumulation factor, and that helps us find C max at steady state also. And then just a general equation, we have C minimum is equal to C maximum times e to the negative kt. This is just the regular equation for IV bolus, and that's what we're really working with in the multiple dose model. And just a side note, this T is not time. Well, it is time, but it's a specific kind of time. It's the dosing interval, and we know that dosing interval is constant. And we always use dosing interval in multiple dose situation. So now looking at the graphs, basically I have the multiple dose. It kind of goes up. It's dose 1, dose 2, dose 3, dose 4, dose 5, 6, 7. And it goes up, and it kind of plateaus, and so we have our C max is here. C max, by the way, is also CO, right? We know that. And then we have C max 2 for the second dose, C max 3 for the third, C max 4 for the fourth, C max 5, 6, 7. And we know that C max 5, 6, 7 are all pretty much the same, right? Because that's steady state. So we can call all these C max SS, and a lot of subscripts, but this is going to become important later on. So now we can kind of refer to these all as C max at steady state, and we're going to use mainly in order to get this, actually it's really easy. All you do is you just do C max 1 or C0 times S, but this S is going to be at steady state. So boom, not bad. And if you want to find C max 2, all you do is you do C max 1 times S at 2, and you get C max 2. So not too bad. And then just minimum, I have on this second graph, I have it all here, and basically you have your C minimum for the first dose, C minimum for the second, C minimum for the third. And in order to find C minimum, you just do the max times e to the negative kt, and you get the minimum. So for example, for let's say for the first one, we have C max 1 times e to the negative kt, whatever t is, and t is this interval right here, that's t, and we know all these intervals are the same. That's t and that's t. So all these dosing intervals are the same. We multiply them together and we'll get C minimum at 1. You just repeat it for the same thing, except for this one, this would be, you would use C max 3, this one you use C max 2. Okay, so I actually want to do a problem. So right here is the problem. So I usually do them last, but I kind of wanted to do it first. So you got a 50 milligram of drug X is given to a patient every 4 hours via IV bolus shot. If their V is 40 liters and half-life of the drug is 4 hours, find S, accumulation factor, find C max. C min at n equals 3 doses and n equals 20 doses. So we'll work with the 3 for now, right? We'll work with the 3 for now. And I kind of just have the equations here for your own reference, So let's write down what we have. So we got your dose is 50 milligrams, right? We have every 4 hours via IV bolus shot. So that's obviously multiple dose. And your dosing interval T is going to be 4 hours. Your V is going to be 40 liters. So we know automatically if we see dose and V together, we know to find concentration, and that's really simple, right? We know the volume of distribution equation, V is equal to D over C, so that translates to V times, sorry, C is equal to D over V. So then we can even just write it down, you know, so we don't have to worry about it later. C is equal to, or CO actually, CO, which is also known as C max 1, you know, just get into the habit of writing all this, is equal to whatever 50 divided by 40 is, and let me see what that is. I'm really bad at math. Okay, so it turns out to be 1.25 milligrams per liter. So we're gonna need that. So we got half-life drug is 4 hours, and we want to find S. So let's find S first. So S, the equation for S is right here. So let me use a different color, and we'll say so Sn, n equals 3, right? Sn equals 3 is equal to 1 minus e to the negative. N would be 3. K is going to be, oh, sorry. See? Just got to convert everything. So K, we know half-life. So we can convert that to K. K is equal to ln 2 over half-life. So basically, K is equal to, K is equal to about 0.173. So you get 0.173, and T dosing interval, big T, I should say, is 4, and 1 minus e to the negative k, you know, kt, same thing, 0.173 times 4, and S, your accumulation factor at 3 ends up being, alright, so our S3 comes out to be, 1.75. So now we have this, right? If we have this, we can find our C max and our C min at n equals 3, because we know our C max 1, which is 1.25. So if we just look at this equation now, really simple. Oh wait, sorry, not this equation. It's actually this equation that I did not write down. So C max n is equal to C max 1 times Sn. So boom, there we go. Alright. So we got your 1.25 times your S, which is 1.75 at 3. So it's important to note this is at 3. Is equal to your going to be your C max at your third dose, and we'll get 2.19 milligrams per liter. So that's that. And to find your C minimum at 3, you use this equation now. So all you do is you have your C max at 3. So let me use different color. We'll say you have your C max at 3, which is, you know, 2.19. You want to multiply that by e to the negative kt. Your k is going to be, we have it right here, 0.173. 0.173 times your t, which is 4, and you'll get your C minimum at 3. So let me see what that ends up being. Alright, so you get about 1.09 milligrams per liter. So that's going to be your C minimum at 3. And just for 20, you just kind of repeat the same thing. But remember, I think I mentioned this in the last video. At 20 is a really big number, right? So if it's a big number, you would just use this instead, this equation instead, right? So you don't have to kind of calculate, you know, consider the n in the numerator. You just use this one instead. But the next topic I want to talk about is actually, so you know, 20 you guys can probably do on your own. You just plug the same process, and we'll get this. Except C max this time isn't gonna. C max, you could say 20, or you know, just more conveniently, you could say C max at steady state, and likewise you'll have C minimum at steady state. Okay, so the next topic I want to talk about is something you guys might have this question, like how do you really know what's a big enough 20? Like when do you know to use this equation? At what n do you use this equation? So I'll get to that, and it's really right here. Okay, so when is n considered big, or I should say big enough, so that we can use this second equation, right? When is n considered big enough? And for your reference, I have these two, and what you need to do is you just need to find a fraction. So this is really similar to what we did in IV infusion, where we find the fraction of the steady state. So we'll kind of just divide it. We'll divide these two numbers, and you know when we divide, we flip it around. So then we'll get 1 minus e to the negative kt in the numerator over 1. And what happens? These two cancel out. So this fraction, right, this fraction, steady state, you're comparing, you know, the steady state S, the steady state accumulation factor, and the, you know, just a regular nth dose accumulation factor. And the fraction ends up being just simply the numerator right here, this number, and that's 1 minus e to the negative n kt. So this is it, man. And if we just manipulate the numbers a little bit, let me see what we get. Alright, so if we mess with this equation a little bit, and we know, by the way, that k is, you know, just ln2 over half-life. If we play with this equation a little bit, we'll get that. I'm not going to do it here, but Xiao kind of did it in class. I don't think it's that important to really know how to convert it, but you basically get 1 minus 1 half, right? 1 half n t over half-life. This is all an exponent. I don't want to put too many parentheses, but this is all an exponent. So this is really the equation you need. And why is that? So let's take a look. So in the last problem, we had our t was 4 hours, and our half-life was also 4 hours, right? So I would say a fraction steady state that's close to S accumulation factor at steady state would be when, you know, Sn is a big number, right? Because triple S is pretty much 100%. So we would want a number as close as possible to 100%. So I would say like 99%, right? 99%. So yeah, so 99 over 100 would just be Sn over SSS. So then our FSS would be, you know, 0.99. And that's pretty close. I mean, you can't really get, you can do like you can make Sn like 99.9999. It's never going to get to 100 really, but it's going to be really close. But for practical purposes, we can say that it's going to be 0.99. So then we just plug everything in, right? And we'll find n. N is going to be our missing variable. We'll have SS, we'll have t, we'll have half-life. And just an FYI, this is an equation that can really, from the textbook, that can really simplify the work you have to do. So if you just do this, right, you just move this equation around, you get n times t is equal to ln, negative ln, it's really bad ln, negative ln 1 minus FSS over k. I remember this helped me on the last test, because it asked us like, it was something, but I remember this helped me. So you don't have to remember it, but it just makes it easier because you don't have to play with the exponents here. You just have the exponents straight out here. So we plug everything in, and actually you can change this k to, you can change this k to half-life, but you know, it's whatever. If you change the k to half-life, you would just you know. So if we plug everything in, let's see what we get. So RT, let's see what we get. Let's just do k actually. So k is 0.173. So we get n, we don't know n, it's 4 hours, equal to ln, negative ln, 1 minus 0.99 for FSS, divided by k. K is 0.173, and let's see what we get for n. So n turns out to be about 6.6, 6.7, say 6.7. So you need 6.7 number of doses for it to really be considered at steady state. So this would have to be multiplied by your dosing interval to really get how much time has to be elapsed, right? So it would be 6.7 times 4 hours as our dosing interval at t is equal to 4 hours, and how much time would elapse in order for us to, really start getting this curve, So after how long does it take? So if you multiply this by 4, you get about 27 hours. So 27 hours has to elapse before you get to your steady state. And I mean, that's a pretty long time. So, you don't really want to be infusing a drug for 27 hours. So we're going to get to the next topic real quick, and let me finish up. And it's going to be your loading dose. So this is just what I was talking about, moving on from the steady state. And it's going to be, okay, it's going to take maybe here 6 dosing intervals to really get to this point, right? This point when you really have therapeutic concentration in the body. So how do we skip all that? So we do a loading dose, and your loading dose is going to be D star. So we shoot the dose straight up to here. So we don't have to. We can skip all this, this little whatever elevation time, and we get straight to the therapeutic concentration. So how do we do that? Well, there's 2 ways to find your loading dose, and let's say we have this value. Number one, the first way is if we have this value, and this value number is Cmax steady state. So if we have the Cmax steady state, and if we have the volume of distribution, all we need to do is use the volume distribution formula. That's V is equal to D over C, and you move that to V times C is equal to D. So your loading dose. So all you do is you multiply C times V and you get your loading dose. That's the first way. The second way would just be to take your regular dose. So I think in the other problem, your regular dose was, that's really bad. Your regular dose is 50 milligrams, right? So you take 50 milligrams and you multiply that by the accumulation factor at steady state, and you should get accumulation factor at steady state. I believe was when N was 20. Doesn't really have to be 20, but we found that out later. And that was 2, I think. So it was 2. All you do is multiply, and you get your loading dose to be 100 milligrams. Same thing with this. You can find, I think, even if we do this, we can verify. I think the last problem was 40 liters. Your CSS, your Cmax at steady state was, let me see. Okay, so we actually didn't calculate it, but your Cmax at steady state is really easy. All you do is you do Cmax 1 times SSS, and that gives you your Cmax at steady state. Your Cmax at your first dose was 1.25, I believe. Your steady state is 2, so you'll get 2.5. It's 2.5 here, and you could already see 2.5 times 40. That's going to be 100. So 100 milligrams. So if we give 100 milligrams of the drug, we'll get the concentration straight up to here. That would be 2. Was it 2? Yeah. No, 2.5. 2.5, because that's Cmax steady state. This is Cmax steady state. So you get, if you give a dose of 100 milligrams, you get it straight up to 2.5. But whereas if we give it 50, it goes straight here. It has to kind of climb up a bit. So you see the difference that loading dose, giving more of a dose can give. That's 100 versus 50. So that's pretty much it for multi-dose. There's a little bit more, but I think it's like AUC, and just practice problems. That's really how you'll get better at this. I remember for the first test, I used to practice problems all in the textbook, and yeah, that helped me a lot. So good luck.